Welcome back. Hi everyone. Welcome to the final tutorial on fluid mechanics lab. So today I'm going to talk about head loss due to sudden contraction and sudden expansion as well. So in this figure we can see that there are a lot of pipes, right? One pipe is connected with another one, and see the diameter are different. So this is bigger diameter pipe, that is smaller diameter pipe, and here you can see one bend, and there we can see another bend, and see this is the smaller diameter pipe connected to bigger diameter pipe. So these are the connections, right? In reality we can see. So this may be the fluid which is oil, or fluid may be different. So we're talking about fluid flow. Fluid may be water, fluid may be oil, fluid may be any liquid, right? Or any gas. So these are combinedly called fluid. So gaseous fluids are called compressible fluid, and the liquid, mostly water, these are basically incompressible fluid, because if you apply any kind of pressure, so it won't change its volume like gas do, right? So different gases has different types of properties, so that is different topic. So we're not going to talk about that gaseous things today. So we are going to talk about only a fluid that is a liquid, and especially since it is basically a civil engineering related course, so we'll talk about only water. So here we can see the pipes are connected with another pipe. So that one, the smaller diameter pipe, is suddenly changing its diameter, right? Either it is contraction or expansion depending on the direction of the flow. For example, we have a pipe here, right? And we have what? We have this smaller diameter pipe. So what will happen if the liquid flows from left to right? Then we'll have sudden contraction here. We'll have sudden contraction, right? We can see that is the contracted section. And what will happen if liquid flows from right to left? The situation is different, right? So it is sudden expansion. Liquid is expanding, so it will flow like this way. So it will be like that. So depending on the situation or depending on the direction of flow, it may be sudden contraction or sudden expansion. And not only this one, we may have this type of elbow, right, bend, or this type of right angle bend. So because of this bend, there will be some losses, head loss. In liquid we call it head losses, right? So these losses are not the same loss that just we calculated only for friction. So frictional loss is mainly because of the roughness of the pipe, right? So that is called measure loss. We know that by this time. But for settings and feedings and bendings and different types of contraction and expansion, we'll have even loss that is not even up to that magnitude that we saw for friction. So that's why these are called minor losses. So there will be two types of losses in liquid flow or in fluid flow. One is measure loss because of the roughness or friction or viscosity, and then we have minor loss because of the settings and fittings. These are the two basic classifications of losses. So today in this experiment we'll try to calculate and try to relate and calibrate the device we have, how to calculate the minor losses, especially for sudden contraction and sudden expansion. So that is our focus for today. Okay. So why this is important? Because we need to carry water. If we just consider water as a fluid or liquid for this case, we want to carry water from a distribution system to the household or industry or anywhere, right? So what do we need? We need to use a bigger pipe from the source, and then gradually we'll even change our pipe diameter, and up to the tap of water we'll use very small diameter pipe. So that's why sometimes we may not use different types of smooth transition. So what do we usually use? We use a pipe and one connecting tube that directly connect with bigger diameter to the smaller one. So that's why there will be some losses. And why it is necessary to calculate the losses? Because if we don't want to lose any head or any pressure at the outlet or any distribution system or any household. So that's why we need to calculate that. Okay, I just discussed about that one, right, previously, that we have overhead tank here, and we're gonna even distribute water at, right, 20 kilometers. So what will happen? We need to be able to supply water there. We have pipe network and we have household and everything there. So if we know that, okay, this is our head loss, so head loss like 50 meter, we lose 50 meter head loss. What does it mean by 50 meter? Means if we have water and the energy is 50 meter, it is related to the 50 meter height of water, so that much energy we will lose, right? The water of 50 meter column can do the same task, right? The energy or the force, so we'll lose that much energy. That's why we'll have very less pressure. We won't lose the amount of water because there won't be any evaporation or any diversion, anything. We're not considering that one. We're only considering the loss of energy, right? So that's why people won't get that much water pressure and that much flow, right? The force. So it will take a long time, and so the flow of water will be very slow. So that is a problem. Sometimes you need very fast flow, we need that much pressure. So that's why you have to be able to calculate even the minor losses as well as the major losses. So if you combine them together, major and minor, then you can even apply your, right, you can increase that amount of head. You have previous head and you have to apply the head loss. Then if you apply that total energy here, then you'll lose this much energy because of minor and major losses, and people will get the expected head. That is the design head, right? So that's why engineer needs to understand what are the losses, major and minor, and which one is important for which purpose. So based on this information, this sudden expansion and sudden contraction is necessary. Other than settings and fittings, we need to know these losses because we'll use this type of sudden contraction expansion joint a lot. So that's why it is very important, and this is the practical application. In order to design any water distribution system, we need to know the losses, including the major loss and minor losses, right, as well. So in this experiment, we have a specific setup, right? So let me quickly even discuss here that we have a pipe that is basically that contraction. We have bigger diameter pipe and we have a contracted pipe, means flow is from left to right with Q. So what will happen if water flows from left to right? Then the streamlines will be converged that way, right? And then it will flow. It will cover the entire diameter of the pipe. But what is happening here? We have a section, right? We saw this type of section for orifice. We call it vena contracta, right? Means the section of minimum cross-sectional area after passing that opening. So it is kind of same thing. We have opening and water is flowing. So it is just converging and forming a contracted section called vena contracta. So the cross-sectional area of the stream or the Z here, it will be lower than there, the pipe diameter. That's why there will be some loss. Suddenly contracting the cross-sectional area, it is just kind of hindrance or obstacle for the flow of water. That's why it will lose some energy, and we are calling this energy loss as head loss due to sudden contraction, and the notation is HLC, right? On the contrary, what will happen if we have the opposite situation like this one? Water is flowing and we have another joint or another pipe that is sudden expansion, bigger. So water will flow then this way, that way, right? And at the same time, there will be something like that. We are calling this as eddies or vortices, right? Eddies or vortices. So because of this eddies and vortices, there will be another loss. So that loss head loss due to sudden contraction, and that loss, head loss due to sudden expansion, these are not the same. So because of extra formation of this eddies or vortices, so there will be more loss. So the head loss due to sudden expansion will be greater than head loss due to sudden contraction. So in this experiment we'll calculate that one, and we'll make sure that, so that's why you need to know where you are losing most of your energy, right? If you know that, and then you can consider while designing the distribution system that, okay, I need to focus on this part or that part, and I can even neglect that settings or fittings. I can only consider this one. So you have to be able to understand. If you even neglect, right, all of these minor losses, but you can't even neglect or omit that major losses due to friction, because you have to be able to calculate, you have to check if the flow is laminar or turbulent. Most of the pipe flow will be turbulent. So for the turbulent flow, you have to know the material of the pipe, and from that you can check the table where it is already mentioned, right, from research and from different experiment, people already found, right, the exact roughness for every material, literally every material. So you can even use that value, F, friction factor, then in order to calculate your measure loss. So you can only consider your measure loss, right? So that's that. So this is the condition or the pattern of flow that usually arise when water flows from a bigger diameter to the smaller one, and we have contraction, and when we have expansion. So let's see the experimental setup, and let's see the mathematical equation. So that this experiment is not that complex, it is pretty simple. Just we have to keep in mind that we have this type of setup. So let me show you that mathematical equation for this one. So we have this setup. We have water that is flowing from left to right, and we have a pipe that is bigger diameter, and we know the diameter there, it is kind of D1, and we have another shorter diameter pipe, it is D2, right? And we have another section. So this section, this pipe and that pipe is the same. That's why see the cross-sectional area, it is A1, and here it is A2. So what will happen if we have Q same, right? So the AV, we know that AV is equal to Q, or Q is equal to AV from this continuity equation, right? So that V is equal to Q over A. So if you have same cross-sectional area, then we'll have same velocity. So that's why the velocity V1 is here and V1 is here. But the pressure, right, P1 and that P3, these are not same, because over this section we'll lose some energy, and the pressure head won't be same, even though the velocity head is same, because velocity is related to the flow rate. And if the pressure is also same, then there won't be any loss. Since there will be some loss, that's why the pressure won't be equal, because we know the total summation should be same, right? So we're considering only a small part of a pipe section. So that setup is not that 1 meter or 2 meter, but in our previous experiment when we calculated the head loss because of the roughness or friction, we consider 1 meter, right, length of a pipe. But for this case we are not gonna consider that. It will be only few inch or few centimeter. That's why we're not considering any significant length of the pipe, and we are just omitting the calculation of measure loss. Right? We are not going to calculate that measure loss again, because we know how to calculate that one if you know the roughness and other parameter of the pipe. So here we are just only considering minor losses. That's why the section of the pipe or the length of the total experiment is not that long, so that we can even omit that measure loss. Only we are focusing on the minor losses. So we can write the experiment, because we know there it will be contraction, and there it will be expansion, and here we'll have eddies or vortices, right? We'll see that. So if I insert one manometer, so these are not piezometer, these are called manometer, and these are basically the mercury manometer. We have mercury here, right? These are the mercury Hg, and we also have mercury here. These are also Hg. We know the mercury is 13.6 times heavier than water. That's why the specific gravity of mercury is 13.6, and for water, right, it is 1. So what will happen? See, the pressure is that is called differential manometer, because this manometer is connected here and here. So what will happen? Water will push this way, water will push that way, and then based on the pressure, water, that material inside that manometer, it will go down, and there it will also go down. So based on the magnitude of the pressure, the length of that downward movement will depends on that force. Since we have bigger diameter here and the pressure, the P by gamma will be higher, right, than this one, P by gamma, that is P2, that is P1. So that's why water is pushing more, we have higher pressure, so it is there, right? And for this one we have less pressure compared to this section, so that's why the mercury level is here. If we take the difference, we don't need to know where it is, we need to know only the difference between these two levels. So that will give us the value of P1 by gamma minus P2 by gamma. So that will give you the value directly. So that will be in terms of centimeter of mercury, the height, or millimeter of mercury. If it is in millimeter, you have to convert it to centimeter or meter, whatever unit you need, you can convert that, right? So, and after that, what do we have to do? You have to convert, because we are measuring the head loss due to contraction and expansion, and the fluid is water. That's why we have to be able to convert that H1 in terms of water column, height of water column. So what we have to do? We have to multiply by S minus 1. So H1 should be multiplied by 13.6 minus 1, and ultimately H1 into 12.6. So that will give you centimeter or millimeter of water, not in mercury. So we're just converting the value of pressure from mercury to water. So what will happen if we apply our well-known Bernoulli's principle in between these two sections to calculate the head loss due to sudden contraction, right? So what will happen? So for section number 1, we can apply P1 by gamma plus V1 squared divided by twice G is equal to P2 by gamma plus V2 squared divided by twice G, and the head loss, we're just denoting this head loss HLC for this section. I'm applying the principle section 1 and in between section 2. So if I want to calculate the head loss due to sudden contraction, I have to write the equation that way, right? So that is nothing but H1, and what I'll have V1 square divided by twice G minus V2 squared divided by twice G, right? But in reality, in experiment, what the relationship is, we just neglect that relationship. But in our experiment, we'll consider only the difference between these two. Okay, it will be a V2, that one. So H1 plus V2, because V2 is important, minus V1 squared divided by twice G. But what happens actually, people conducted different types of experiment, and they got a relationship that is called K V2 squared divided by twice G, and the value of K should vary in between 357 to 0.5 because of that contraction. So we don't need to measure the value of V1, or we can exclude the approach, right, pipe section of the pipe, or the velocity. We only need to consider the velocity at which we are gonna measure the head loss because of the contraction. So we need the diameter of the contracted section or the smaller diameter pipe, right? So we can even assume that maximum value in order to be on a safe side, right? So V2 squared divided by twice G, we can use that formula in our experiment as well. We don't need to even measure the pressure differential, because the pressure in between these two sections sometimes we don't need that. So we can use this formula, and from our experiment we can even use that formula as well. If we have that manometer set up, we can use the manometer reading, and then we can use the velocity head, difference of velocity head. Then we'll have the head loss due to sudden contraction. We'll check both equation as well. Sometimes because of your setup, maybe you'll get negative head loss, not for this one but for expansion. So that's why we have to avoid this type of issues. So that is because of contraction, and let's see what will happen if we apply the same Bernoulli's principle for expansion, right? Same expansion. So we are going to apply the same equation for these two sections. Here it is the same section number 2, I'm assuming that's section number 2, and there we have the manometer, section number 3. So the same equation, P2 by gamma plus V2 squared by twice G is equal to what? P3, right, by gamma plus V1 or V3, whatever it is. For this one it is same, so we can write that way, and the head loss will be due to sudden expansion. So similarly we can write that equation, head loss due to sudden expansion is equal to P2 by gamma minus P3 by gamma. So that will be H2 for our experiment for today, and plus V2 squared by twice G minus V1 squared divided by twice G. But again, from experiment and research, from people identified what? People identified the same relationship, but this time it is V2 minus V1 squared divided by twice G, and we have K1. So that is the head loss because of the sudden expansion. So there the value of K1 is unity 1. Okay, so we can use that formula. See, there it is difference of what? It is difference between the velocity head, but here it is the difference between the velocities in between two sections, right? For this section and the expanded section, and then we are taking the square and then dividing by twice G. So we are just taking the difference between the velocities, and then we are calculating the velocity head, and we are multiplying this with a constant K. So this is how we can calculate the head loss due to sudden expansion, and that head loss due to sudden expansion must be greater than head loss due to sudden contraction. So from our experiment we'll measure the pressure differential and we'll calculate the head loss that way, and we'll also try to develop an equation like this one and also the previous one. So head loss due to sudden contraction, we saw that was like K and V2 squared, right, divided by twice G. So we are gonna call it C1 and V2 to the power n HLC as before, right? K divided by twice G, we are considering that as C1 because these are constant. So we'll calculate the value of n and C1 as before, right, from a log paper, graph paper, because if we have several values of head loss due to sudden contraction for different flow condition, and then if we have several velocities V2, then we can plot it, we can calculate as before. So similarly we can do the same thing for expansion as well. So we can write that formula C2 and V2 minus V1, and that will be M, right? So from this formula we can calculate even M and C2 from log graph paper. So we'll plot V2 minus V1 against, right, we'll plot HLE against V2 minus V1, and we'll calculate the slope and the coefficient C2. Then we'll have the empirical formula, right, the calibrated formula as well. So that is the objective, right, to calculate the head loss due to sudden contraction and sudden expansion, and then to calibrate this or these equations as well, right? So that's that. So let me just try to show you that objectives to determine the head loss due to sudden expansion and contraction, and to plot and calculate those values. And we have one practical questions that for the same diameter ratio and the same velocities, the loss due to sudden expansion is greater than, right, the loss due to corresponding contraction. So why is that? We mentioned that one, right? If we have sudden contraction, so there will be only vena contracta, right? Only there will be vena contracta. However, when it is related to sudden expansion, so other than we'll have vortices, right? So we'll lose more energy because of that formation of vortices and eddies. So that's why the head loss due to sudden expansion is greater than head loss due to sudden contraction. Okay. So let's go to the calculation part. So we have, as before, this data sheet. So we need to know the diameter at the bigger diameter. These are same for section 1 and section 3. So the diameter is given 1.77. If it is not given, so it will be given a length, shorter length of a pipe, and then you have to be able to calculate the internal diameter of the pipe using slide calipers. If you know how to use slide calipers, right, you have to be able to measure that value, right? So there are two different parts of the slide calipers that measure the external diameter or the internal diameter. The smaller portion of the right slide calipers that is tossed at the up, right? If we have the slide calipers scale like that, so we have like that one slide caliper, so we have this part, so that part will measure the internal diameter. So that's that. You have to, if you know that, it's easy. So we have the diameter d1, we have to calculate the area, right? We know the equation of a circular section. So a1 will be pi divided by 4 d1 square, right? So what will be the value of this one? So I'm just going to show you the complete. So 1.77 squared, 3.1416 divided by 4 multiplied by 1.77 and squared, so we are going to get 2.4605. that will be centimeter squared. And we have a2, so let me quickly calculate that one as well. So 3.1416 divided by 4 multiplied by 0.74 squared. So we have the smaller diameter, 0.4300 centimeter squared, right? And the total volume of water, when water is flowing, right, whether it is contraction or expansion, so what is actually happening? We're collecting the water in a tank, and the total volume was 10 liter, right, when we started the experiment and when we stopped it. So it was 10 liter, that's why it is 10 liter. So we know the relationship between liter and the meter, right? So 1 liter water or liquid is equal to what? Because you know that 1000 liter is equal to 1 meter cube, right? So it will be that much. So that's why if we have 10 liter and 1 liter is equal to even 1000 centimeter cube. So that's why we have 10 liter. So 10 multiplied by 10 to the power 3 means 1000 is equal to 10 to the power 4 centimeter cube, right? So that is the value, and we measured the time. So to collect water for 10 liter, water of 10 liter, it took like 18.7 seconds. So that is the second. We know the volume V and we the time T. So what will be the flow rate, right? So it is 10 to the power 4 divided by 18.7. It will give you 10 to the power 4 divided by 18.7. So it will give you 534.6 2.75 centimeter cube divided by second, right? So the velocity, now we have to calculate the velocity. It is a centimeter per second. It will be centimeter per second. So let's see, we know the q, right? Now we know the q, we know the cross-sectional area, so we can calculate the velocity. So v1 will be q divided by a1. So the q, we know it is a 534.76 because 75976, and divided by 2.4605. So that will be 2.4605, and it will give you that value. I'm directly writing there, 217.34. And what will be v2? v2 will be same, q divided by a2. It will be higher, right? 534.75 or 76 divided by 0.4300, and we are gonna get, it is 12 for 3.63. So the velocity at section 2, when we have a smaller diameter pipe, the velocity is pretty high compared to the bigger diameter pipe, right? So that's why there will be some losses. And we have the reading H1, right? That mercury manometer, it is in terms of mercury, it is 19. And we have another at section 2, the difference between P2 by gamma minus P3 by gamma, we have H2, it is 1.5. So we can calculate that, right? So if we multiply that H1 into 12.6, we'll get in terms of water, right? So that will be 239.4. Okay, so that will be H2, and if you multiply that by H2, I think that reading is not accurate, maybe. Let's check. 18.9. So head loss due to contraction, right? So we just saw the calculation that HLC, that will be H1 plus, from the experiment, I'm talking about the experiment, that will be V1 square divided by twice G minus V2 square divided by twice G. If we take that, it will be negative, right? But head loss won't be negative. So that's why they excluded that part. And they use only V2 and multiply this by that coefficient. But what we can do, we can take only that absolute difference between these two, head loss, the difference between these two. Okay, so what will happen, it will be 239.4 H1 now plus the difference between these two, the absolute difference between these two, V1 217, velocity V1 217.34 squared minus 1243.63, 1243.63 squared and divided by 2 into 981, because this is common for both. So let me calculate 217.34, no, first 1243.63 squared minus 217.34 squared divided by 2 divided by 981, because the acceleration due to gravity is that. Okay, so you are getting very big number, plus 239.4. See, we are getting that much, 100363, that centimeter, right? But that is not true. I think we have erroneous reading here. That is not correct. So that's why we don't need to even consider that part. we'll calculate only based on that. HLC is equal to 0.5 V2 squared divided by twice G. Okay, we'll use that formula. So 0.5 multiplied by 12 for 3.63 squared divided by 2 into 981. So 12 for 3.63 squared divided by 2 divided by 981 and multiplied by 0.5. Okay, so we have that value 394 centimeter. Okay, so that is the value 394 centimeter. 394, so that will be centimeter. So head loss due to sudden expansion, we can use that formula as well, right? And we can use our previous formula. I'm just checking both calculations. So HLE, you know that it should be H2 plus the same difference we just mentioned here, that V2 squared divided by twice G minus V1 squared divided by twice G. It will be the same value, right? These values are same for both, but we won't use that. Let me just quickly calculate the value. It is 18.9 plus, now V2 is nothing but 217.34 squared minus 1243.63 squared and divided by 2 into 981. So that's the same value. And see if we use, oh no, it's this opposite we have. So that is V1. Okay, that is not V2. So that is V2. 12 for 3.63 squared minus 217.34 squared. Whatever it is, we can take the difference only, but it won't give us that much. 12 for 3.63 squared minus 217.34 squared divided by 2 divided by 981 and plus 18.9. So we are getting HLE is equal to 783 centimeter. But if we use that formula, right, that's why they are not gonna use that difference. From the experiment, people are using that K1 and V2 minus V1, and then they're taking the squared and then 2G. So we'll use the same formula where K1 is 1. So we'll have 12 for 3.63 minus 217.34, then it is squared because we have 1, right, for K1, and 2 is multiplied by 981. So let's see, 12 for 3.63 minus 217.34, taking the difference, squaring it, dividing by 2, and then dividing by 981 and multiplying by 1. So we are getting 536.8 centimeter. So it compare this value with the value we have from that equation. So which one is greater? So head loss due to sudden expansion, right? That one is greater than that value, 536. So 536.8 centimeter. So if we just calculate these values, V1 for different flow rate, right, for different groups, we have 5 groups, and if you calculate the same velocity V2 for all of them, and if we take the difference between these two, because we know that we need to take that difference and we have to plot that, then these are the velocity difference we have. And if we calculate the head loss, so that will be due to contraction 394 and 536.8. okay, and if we plot to calibrate that equation, right? HLC is equal to C1 and then V2 to the power n. So we have to plot HLC, head loss due to sudden contraction, against a V2, right? And the another one will be HLE is equal to C2 and V2 minus V1 to the power m. So let's plot, right? I plotted as before. So that is V2 minus V1 here, and we have head loss due to sudden expansion, and we have this line, and from this straight line we have to extract 2 points as before. Okay, so let me select one point where I can't even consider any point, so I can take, which point I can take? That one. Okay, I can take this point, okay, because I know at least one, right? This line is on that line, so I can even draw straight line here. One, I can read that one because that is 100, 200, 3, 4, 5, and that is 600, and we have to read that one as well. See, so you have to read this point. So that is 100, 200, that is 3, so that will be 2 and 250, so 260. Okay, 260. So that's why you have to be able to find a point where we have the intersection, but sometimes you may not have. So what will be the first point? It is 600 and 260. The value of 600 is V2 minus V1, and 260 is the head loss due to sudden expansion, that is centimeter. Then let's find another point. So I'm gonna grab that point. Okay, that point, it is on 1000, right? And there, you know, that is 1000. Okay, that is good that it is 1000, but what will be this point? Let me just find. So what will be that one? So you know that we have 1000 at least, and here we know that is 300, 400, 5, 6, 700 and 8, so 740. Okay, 740. So from these 2 points we can calculate the value of n, right? So you know the log, and then it will be 260 divided by 740 and divided by log 600 and divided by 1000. Let me calculate that. What will be the value? Log, right? Log 260 divided by 740 divided by log 600 divided by 1000, and we are gonna get, see, 2.047. So what was the value of 2? What is the value of n, right? The theoretical value was 2, v2 square, k v2 square. So from that we got 2.047. That's okay, and we can use this point to calculate, because we know that HLC is equal to C1 and V2 the power n. So for this case n0 2.047. If we use this point, and that is the HLC, so it will be 260 minus is equal to C1. V2 is V2 minus, oh, this is not that, it is HLE formula. We are using V2 minus V1, so it is HLE is equal to C2, and that is basically M. C2 V2 minus V1 power 2.047. Okay, so we are just doing the second thing first. So 600, we have 600 to the power, it is C2, 2.047. So what will be the value of C2? C2 will be 600 to the power 2.047, right, and 260 divided by that whole answer. So C2 is 5.326 into 10 to the power minus 4. So the empirical formula we have HLE is equal to 5.326 into 10 to the power minus 4 V2 minus V1 to the power 2.047. So that is the empirical formula for head loss due to sudden expansion, right? So similarly, we have the other plot. We are plotting V2 and head loss due to sudden contraction, and we have the same type of plot. From this one we have to extract two different points. So let's consider first that one. It is looking like reasonable, middle of the point. So we have that, okay, this point. So 100, 2, 3, 4, that is 500, okay, and we have that value. So that is 90 and 100, so that will be like 92 or something like that. So we have first point 500 and then 93. That's it. Let's find another one. So I'm gonna go with this point. It is located right as before on that 1000. It is not like that. Okay, let me grab that way. So we have 1000 here, and that is, I think it is at the middle. 100, 200, 3, 4, so 350, okay, 350. So we have 2 points. We can calculate the value of n this time. So log 93 divided by 350 and log 500 divided by 1000. So let's see what we are gonna get. So log 93 divided by 350, okay, and divided by log 500 divided by 1000 means 0.5. That's okay. So it is nothing but 1.912. So this time n is 1.912, close to 1. So that's okay. The actual value is 2. So let's find, because we know that HLC is equal to C1 and V2, right? The power is 1.912. So we can use the first point as usual. So that will be 93 is equal to C1 is unknown, V2 is 500 to the power 1.912. So the value of C1, 500 to the power that one, and 93 divided by total answer. So we're getting 6.425, 10 to the power minus 4, right? So we have the empirical equation HLC 6.425 into 10 to the power minus 4 and V2 to the power 1.912. So that is the formula for head loss due to sudden contraction. So you know the head loss due to sudden contraction and sudden expansion, right, by this time. So this is how we can calculate both head loss due to contraction and expansion. So that is the, I think, final calculation. We don't need anything. So this is how we can calculate any data we need and anything we need to calculate, right? So that is the end of the even the whole course. We already right, we calculated different values for 9 experiment from standard of pressure to this head loss due to sudden expansion and contraction, right? Can you remember all these names, what we did? So at the beginning we have the standard of pressure, and then we have Bernoulli's principle, and after that we use Bernoulli's principle to develop a device called flow through a venturimeter, right? That is called flow measuring device. And from venturimeter, we have another updated device called orifice. And from orifice, we have another improved device called flow through through an external cylindrical mouthpiece, right? And after that mouthpiece, what we have, we even use weir, flow over a broadcasted weir, and then we have another flow over a V-notch, right? V-notch is the most useful device that can measure flow for a wide variety of head, right? We saw that, and after that we calculated head loss in a pipe, or friction in a pipe, means head loss due to frictional effect or roughness. That is the major loss. And finally today we just covered head loss due to sudden expansion and contraction. So all these losses are because of that settings and feeding. So that is the end of the tutorial series. At the same time, even end of this experiment as well. So in every experiment, what we try to focus, we just try to describe the theory a little bit, and then because this is not the theory class, right? It is lab class. So if we already have idea about the theory, then we are gonna just apply this knowledge. So I'm just reviewing everything, right? In the fluid mechanics class or in theory class, you will know this in details, right? That's why I'm just reviewing quickly by assuming that you know all of these equations and the logic or theories behind this, all these assumptions as well. But I repeat so that you can even remember that what you have learned previously regarding that specific theory or experiment, okay? So we try to focus on the theory, we reviewed that, we try to see what are the practical applications of that specific experiment, and then we saw the necessary equations for calculating the specific parameters or unknown for this experiment, and we plotted necessary graphs on a log graph paper or on a plain graph paper, right? And we calibrated that specific device, and we even calibrated the formula, and after that we even plotted the calibration curve. So once you have these things ready, you can paste the equation, or you can use, right, our calibration curve to find the unknown values. For this case, what is the most unknown values we want to know? It is sometimes flow rate, or what is the discharge, and sometimes it is head loss. These are the most important, right, variables or unknowns from this experiment. So I'm not gonna even extend the video anymore, so I'm gonna finish it here. So if you have any query, any confusion, you can go back to your theory class, or you can even review fluid mechanics book that you already might have, and if you have any query, so you can ask your instructor, or even you can shoot any comment there in the comment box. So I'll try to get back to you, because I'm just trying to make the video short, but I didn't show how to take all these readings from the experimental setup, because I can't show you this one. So what I try to show, right, I just showed the experimental setup, the pictorial description, and you can go to your lab, you can take the readings, but this series of tutorial will help you to calculate, right, and how to plot graphs and how to calculate. So that will be helpful, I guess. So that's that. So thank you very much for watching all this series, and if you need any help, let me know. And until then, so stay safe and take care of yourself, and learn new things. It's a good idea. So goodbye. Thank you very much.